Welcome to Brain Fuel, where curiosity never sleeps. Today, we're diving into one of the most mysterious and mind-bending phenomena in the universe: black holes. Invisible, powerful, and utterly strange. They bend space, slow time, and defy the laws of physics. But what exactly are black holes? How do they form? What happens if you fall into one? And can they really evaporate over time? Buckle up, because today we're going deep into the heart of gravity itself. Let's explore how black holes work. At its core, a black hole is a region of space where gravity is so intense, nothing, not even light, can escape. That's why we call it a black hole. It doesn't reflect or emit light. It's completely dark. But black holes aren't holes in the way we think of them. They're extremely compact objects. Imagine compressing the mass of our entire sun into a sphere just a few kilometers wide. That's the kind of density we're talking about. This makes the gravitational pull around them unimaginably strong. We detect black holes not by seeing them directly, but by observing how they affect nearby stars, gas, and even space-time itself. A black hole has three main parts. First, the singularity, the very center. It's a single point where all the black hole's mass is concentrated. It's infinitely dense, and physics as we know it breaks down here. Second, the event horizon. This is the boundary around the singularity. Once something crosses it, it can never escape, not even light. It's like the edge of a cosmic waterfall. Once you're past it, you're gone. Third, the accretion disk, a swirling cloud of superheated gas and dust orbiting the black hole. As material falls in, it heats up and emits powerful X-rays. That's often how we find black holes in space. So even though we can't see a black hole directly, we can see the chaos it causes around it.
So how do black holes actually form? The most common way is through the death of massive stars. When a star much more massive than our sun runs out of fuel, it can no longer support itself against gravity. The core collapses under its own weight, triggering a massive explosion called a supernova. What's left behind can be a neutron star, or if the star was massive enough, a black hole. These are called stellar mass black holes, and they can be a few times the mass of our sun, but compressed into an incredibly small space. There are also supermassive black holes, millions or even billions of times more massive than the sun. They sit at the centers of most galaxies, including our own Milky Way. How they form is still a mystery, but scientists believe they may have grown over billions of years by swallowing stars, gas, and merging with other black holes. And then there are intermediate black holes, somewhere in between. Some scientists also hypothesize the existence of primordial black holes, tiny ones that could have formed in the early universe right after the Big Bang. Now, what happens if you fall into a black hole? First, as you approach the event horizon, time would begin to slow down, at least from the perspective of an outside observer. To someone watching from afar, you'd appear to freeze at the edge, your image slowly fading. But from your point of view, time feels normal, and once you pass the event horizon, there's no going back. As you fall deeper, the gravitational pull increases dramatically. Your feet would feel a much stronger force than your head. This difference in gravity would stretch your body like spaghetti, a process scientists call spaghettification. Eventually, you'd be crushed out of existence at the singularity, At least that's what general relativity predicts, but nobody really knows because no one has ever returned to tell the tale. Black holes don't just destroy. They also play a vital role in the structure and evolution of the universe. Supermassive black holes seem to regulate the growth of galaxies. When matter falls into them, it can generate powerful jets of energy that shoot out at nearly the speed of light. These jets can affect star formation and shape entire galaxies. Some of the brightest objects in the universe, quasars, are powered by black holes. As matter falls into the black hole, it gets so hot and bright that it outshines all the stars in the galaxy combined. Black holes also give us clues about the fundamental nature of reality. For example, they help us understand how gravity interacts with time and space. Einstein's theory of general relativity predicts how space bends around massive objects, and black holes push that idea to the extreme. But there's a problem. General relativity breaks down at the singularity, where gravity becomes infinite. That's where quantum physics should take over, but right now we don't have a working theory that unifies gravity with quantum mechanics. This is one of the biggest open questions in science. One breakthrough came from Stephen Hawking in the 1970s. He proposed that black holes aren't completely black. According to quantum theory, pairs of particles are constantly popping into existence near the event horizon. Normally, they annihilate each other instantly, but if one falls into the black hole while the other escapes, the escaping particle carries away a tiny bit of energy. This is known as Hawking radiation. Over vast periods of time, this radiation could cause a black hole to lose mass and eventually evaporate completely. So, black holes might not be eternal after all. But this leads to another puzzle. If black holes can evaporate, what happens to the information inside them? Does it vanish forever, breaking the rules of quantum mechanics? This is called the black hole information paradox, and scientists are still trying to solve it. So, where do we go from here? Black holes are no longer just cosmic monsters hiding in deep space. They're essential to our understanding of gravity, time, quantum mechanics, and the very fabric of the universe. Scientists continue to study them using powerful telescopes, computer simulations, and even gravitational wave detectors. In 2019, humanity saw the unseeable for the first time. The Event Horizon Telescope captured an image of the shadow of a black hole in the galaxy M87. That iconic orange ring made headlines around the world. It confirmed Einstein's predictions and opened up a new era of black hole science. In the future, we might detect evidence of wormholes, travel through simulated black hole environments, or even use black holes to study alternate dimensions. Maybe, just maybe, they hold the key to a deeper theory that unites the laws of physics. For now, they remain one of the universe's greatest mysteries, invisible giants, hiding in plain sight, shaping galaxies, and challenging everything we thought we knew about reality. And that's the magic of science. Every answer leads to more questions. Thanks for watching Brain Fuel. If you enjoyed this deep dive into black holes, don't forget to like, subscribe, and fuel your mind with curiosity. Until next time, keep exploring.